All right, good evening, everyone, and welcome back. Tonight, I'm going to be talking to you all a little bit about what I actually do for a living, and that is the study of galaxies using a technique known as galactic archaeology. So, for the purposes of this talk, I'm again going to be using Slido to make it a little bit more interactive, so you can join along and ask questions and take part in any kind of polls that I run as well. And you can do that just by going to slido.com and using the event code #Galaxy. As we can see, we already have one question from David Corey, which is really more of a comment, asking if I describe myself as an intergalactic Indiana Jones, and essentially, yes, I do. Good. So if you want to ask questions as you go along, I'll be checking them, so they'll be moderated, and I'll be adding them into the live discussion as and when I get the chance. Good. So let's get on with the show. So today I want to talk to you about what I do, which is trying to understand how galaxies like our Milky Way form. So this here is a picture of what we think our Milky Way looks like. Now it's a picture of what we think it looks like because we live roughly here in the galaxy. So we live inside the galaxy, which means we can't really see what it looks like from above in the way that we can in this picture here. We can really only look through the disk, this beautiful spiral disk that makes up our galaxy. But when we do this, we can get some idea of what the structure may look like, and this is roughly how we think our galaxy appears. So in the centre here, you have this kind of long, thin bar, and attached to the ends are these spiral arm features that you can see come spinning out there. And we live inside some of these sort of spiral features, and we orbit around the centre of the galaxy very, very fast, actually. So we're about 24,000 light years from the centre of the galaxy, if I've done my maths in my head correctly. And we spin around at a speed of greater than 200 kilometres per second, orbiting around the galaxy. And that's our position within the galaxy, so that's our home where we live. Now, one of the big questions that we have in astronomy generally is asking how do galaxies form? And so really we want to know how all galaxies form, but we also have a vested interest in learning how the Milky Way formed. And that's because it's our galaxy, and we're quite selfish, and we'd like to know how we specifically got here. So it's one of the key questions that we try and address in astronomy is how do these galaxies form? Now we know there's many more galaxies than merely just our own Milky Way. Essentially, if we look out into space, we see that galaxies are literally everywhere. And this is a picture, it's one of my favourite pictures, that was taken with the Hubble Space Telescope, which essentially demonstrates this. So this image is known as the Hubble Ultra Deep Field, and it's an exposure with the Hubble Space Telescope on a seemingly empty patch of sky that's taken for about 1 million seconds. And it's a tiny sliver of the sky. It's about if you compare the size of this field to the entire sky, it's about 1/26 millionth the size of the full sky. And when we look into this deep, beautiful images, we can see lots and lots of galaxies. There's about 10,000 galaxies in this image alone. And we can see very far back in time to very distant, very faint galaxies in the early universe. And we still know that we can't see all the galaxies because some of them will be too faint for us to detect in this image. But it gives us an idea that galaxies are everywhere and there are lots of them. And in fact, recent estimates put the number of galaxies within our observable universe at somewhere of the order of 2 trillion. So there's 2 trillion-ish galaxies within the observable universe. And that's a really big number. And we'd like to know where these all came from and why do they look the way they do. So 2 trillion is huge, and if you were to write it down, this is kind of what it looks like. So there's 2 trillion galaxies, one of which is our Milky Way, which looks like this. And by and large, we think we live in a fairly typical galaxy. There's lots of spiral galaxies like ours in the universe, and actually something like 70% of all the stars in the whole universe live in spiral galaxies, kind of similar to the Milky Way. So they're somewhat very important for us to understand because it seems like, a lot of stars live in galaxies like this. Now, galaxies like our Milky Way have something on average of about 100 billion stars. So if we look at all the galaxies in the universe and assume that they all have roughly 100 billion stars, that means in the observable universe, there are this many stars. And I don't have a name for how big a number this is. That's a 2 with 23 zeros. So it's an awful lot of stars in the universe. And ideally, we'd like to know where each one of them came from, how they formed, basically what they're doing. And so that's what we're aiming to do as astronomers, is to piece together this whole puzzle of how you get this universe so full of galaxies and stars, and learn about how everything is growing over time. So how did all of this stuff get there? And why does our galaxy look the way it does? Why are we in one of these beautiful spiral galaxies right now? And how did it form? Now we have a rough timeline for how everything sort of happened in the universe. And I say rough, it's actually a fairly astonishingly precise timeline in many ways, given what we have to work with as astronomers. But this is it in a nutshell. This is an image taken from the Planck survey to sort of describe how the universe grows with time. So on the left-hand side of this image, we start with the Big Bang, which began our universe 13.77 billion years ago. And then on the right-hand side, we have today, where our Milky Way and we all live. So between the Big Bang and today, a lot of stuff happens. So first of all, I think one of the cool things about our universe is that we'll never really be able to see the Big Bang. We can only ever see its afterglow. So the first thing we can observe in the universe, and as far back as we can look, essentially to learn about it, is what happened 375,000 years after the Big Bang. And that's the first time that light was able to freely travel through space. Before that, all these light rays that may have been emitted and created were immediately reabsorbed because the universe was so hot and so dense that light just couldn't travel freely through the universe. So we had to wait for the universe to cool down a little bit after the Big Bang and get, sort of low temperature enough and low density enough that light could start streaming through the universe. And when that happened, that was essentially what creates what we call the cosmic microwave background, this afterglow of light that is essentially the radiation left over from the explosion that started our universe. And we can still see it in the sky, all over the sky, in fact, today. So it's much cooler now because it's been 13.77 billion years since we had the Big Bang. But if you look at the sky in the microwave band, we can see this leftover radiation, and that tells us about sort of the initial conditions of the universe. So what did it look like when it first began? And that's as far back as we can go. So after this light was released, structure could start growing, and we start to build galaxies, first of all from sort of dark matter structures, which capture all the regular matter and form beautiful galaxies and stars. And then those all develop over time, and in the end, you get a Milky Way. Now, I just glossed over a large portion of this diagram by just telling you that stuff forms and you end up with a Milky Way. And that is, of course, what we're trying to learn about more precisely in astronomy. What happens in this middle point between the Big Bang and ending up in the Milky Way today? How do we go from that to there? So how precisely do we end up with a Milky Way galaxy that looks like ours? And there's sort of, broadly speaking, two different types of techniques you can use to learn about how galaxies evolve with time. And I'm going to be talking mostly about one, which is what I do, which is Galactic Archaeology, but I'll just briefly tell you what the other approach is as well, because it's cool and they're both very complementary actually. So we can learn a lot by combining the two as well. So the first method is essentially time travel, which is basically all of astronomy. So you probably know that whilst light is the fastest thing in the universe, it can travel at speeds of 300 kilometers per second. I think, if I've done the maths right in my head there. Someone will tell me if I haven't. It can't travel infinitely fast, which means it takes it time to go from point A to point B. So this is even true for when we look at the sun. So the sun is 93 million miles away from us, and we don't see, it takes time then for the light from the sun to leave the sun and arrive here on the Earth. So every time we look at the sun, we're looking into the past. So I just thought I'd maybe start with my first poll right now. So how long do you think it takes for light from the sun to reach us here on the Earth? So if you want to join in with this poll, just go to slido.com and use that event code #Galaxy. And then you can select from the following options. Does it take 40 seconds for the light to reach us, 8 minutes and 20 seconds, 23 minutes and 40 seconds, or 3 hours and 20 minutes? So yeah, just have a guess. Or if you know the answer, pick the right one. While you do that, I'll take a look at some of the questions that you've been sending in. Give you a little bit of time to think about that. Right, so I think I started you off with a nice easy one. So it seems like you're all converging or mostly converging to the right answer here. So it takes light from the sun about 8 minutes and 20 seconds to reach us here on the Earth. So that's about how long it takes for it to travel 93 million miles. Now, that means whenever we look at the sun, we're essentially seeing it as it was about 8 minutes ago. Now, of course, when you move to further away things, that means it's taken even longer for the light to reach us. The next nearest star after the sun is something like 4 light years away. So that means it's taken the light from that nearest star 4 years to reach us. And then, of course, as you go to galaxies, it becomes longer and longer still. So this next picture is of the Andromeda Galaxy, which is the nearest massive galaxy to us. Essentially, it's in our back garden, you could say. It's incredibly nearby, so we can study it in great detail. We basically think of it as being in our neighbourhood. So I guess the next question is to ask you, how long do you think it takes for the light from Andromeda to reach us here on the Earth? So again, you can choose from these options here. Do you think it takes 2,500 years, 250,000 years, 2.5 million years, or 250 million years? So we already have one vote for 250 million years. I'll give you a little bit of time again to have a look at that. So this one's a little bit more divided, it looks like. All right, so it looks like around about just over half of you think it takes 2.5 million years for the light from Andromeda to reach us. About 30% of you think it's going to take 250 million years, and then 12% think 2,500 years, so quite the extremes there as well. So the actual answer to this question is that it takes 2.5 million years for the light from Andromeda to reach us. So every time we look at this galaxy, which is actually the one that I spend most of my time studying, everything I'm looking at there is about 2.5 million, happened about 2.5 million years ago. So it's 2.5 million years ago into the past. Now, in astronomical terms, that's not very long ago. So people who study much more distant galaxies would tell me that 2.5 million years ago is essentially the same as today. There's basically no different in those two times. It's not very far away at all. So they would often, if you're studying galaxies much further away, you can get way further away and look at things that were formed much longer ago, that have emitted their light and has travelled all the way to see us now on the Earth. And this is an image of the most distant galaxy that's been observed, and therefore the one that's furthest back in time. And it's an object called GN-Z11, and it was observed with the Hubble Space Telescope. And we believe that the light left this galaxy about 13.4 billion years ago, which is only a few hundred million years after the Big Bang. So that's the most distant thing we can see, and it's actually even further away than that as well, because the light left it 13.4 billion years ago. But in that time, the universe has expanded, so it's even further away from us now than it was when it emitted this light. So that's sort of the furthest back or furthest away we can look at galaxies. But we can look at all the galaxies in between that as well. So we can probe and take images and make observations of galaxies anywhere from sort of now, today, all the way back to 13.4 billion years ago. And given that there are so many of them around, it means we can build up what the populations of galaxies look like as a function of time. So did galaxies that were forming 10 billion years ago look the same as the galaxies that we have now? Or can we see how those galaxies have sort of changed and morphed into the ones that we see today? Can we build up a timeline by looking further and further back to see how the galaxies have been changing over cosmic time? So this is essentially what we're doing with this time travel approach. You're just taking snapshots of the universe at different times to see what the population of galaxies looked like, and then trying to thread together what that means for galaxy evolution by assembling all these images at different times. So this is an example of one such study that was done with the Hubble Space Telescope, I think by Van Dokkenmiddel. And it's basically how a Milky Way galaxy, or a Milky Way-like galaxy, so something like our galaxy, is formed over time. So on the left here, we have the most recent image. So this is a galaxy that's light left it about 3.1 billion years ago. And you can see it looks kind of like a spiral there. And then as we move rightward, we go back all the way to sort of 11.3 billion years ago. So you can see then, at each of these epochs, what the Milky Way might have looked like in the past. It obviously isn't the Milky Way itself in the past, but it's objects that could conceivably turn into the Milky Way today. So it gives you some idea of the range of ways you have to build up something that looks like the Milky Way at the present time. So that's really, really useful and allows you to do like a great population statistics. So a really good idea of in general how galaxies grow. But we also know that means that there are many different ways that you could form a Milky Way galaxy. So it doesn't give us a precise map of how our galaxy formed. And of course, the further you go back in time, the less you can actually see in these galaxies. So for the one, for example, on the far right here, you can make out that maybe it's slightly disky shaped, it's kind of a bit red in colour, but you can't see a lot of detail like you can at this one image on the left or even for our own galaxy. So there isn't as much information in the data as we would like to really get like a fully detailed picture of how the Milky Way grew over time. So to get around that, we can just study the Milky Way in extreme detail to try and learn about its history. And we expect that it will change from galaxy to galaxy. So even if you had two Milky Ways, they may not form in the same way, and that's because galaxy formation is quite messy. And it will be slightly different from galaxy to galaxy. And we know this from both observational studies, but also studying computer simulations. So when galaxies grow, essentially the seed for galaxy growth comes from the dark matter that we have in the universe. So we know that our universe is made up of mostly dark matter compared to ordinary matter. So ordinary matter is anything that we can see and touch. So, anything like us, the planet, stars, gas, all of that is ordinary matter. Then dark matter behaves a lot like normal matter in that it exerts gravity, it has mass, but it doesn't interact with light at all, so we can't see it directly. But we can study it and find out that it's there, or it seems like it's there. And it seems like there is about 6 times as much dark matter in the universe as there is regular matter. So if we can understand how the dark matter grows over time, we can actually understand what the normal matter is doing, because it will just follow the dark matter, because the dark matter drives everything. It's like a seed or a scaffolding on which the universe is built. So this simulation starts off with an almost evenly distributed cloud of dark matter. So this is this box here that you can see that's very large on the side, 10 megaparsecs, and I've written down what that is in miles as well, so a really big patch of space, starting early in the universe. And some patches of this dark matter have a little bit more dark matter than other patches. And because they have a little bit more stuff, it means that they'll grow more over time and attract more dark matter from the surroundings to themselves to make bigger and bigger dark matter halos, as we call them, and it's in these halos that galaxies will live. So I push play, you can see this happening. So the areas that had a little bit more dark matter start to have more and more dark matter as time goes on, because they just start merging with nearby clumps of dark matter. And when they do it, they make this really beautiful structure, this sort of cosmic web, as we call it, a bit like a spider web or a cobweb, where they attract smaller bits of dark matter along these wonderful filament structures, or these sort of webby features. And this is what the gas and the stars will follow as well, because this is where most of the mass is going. So most of the gravity is acting where the dark matter is. So if we run the same simulation, but instead of looking at the dark matter, we look at the regular matter, we can see that it does the same thing. So all these clumps of stars and gas, which is what you can see in this simulation. So where it's red, you have more stuff. In this case, it's gas. And each of these little clumps are like small little proto-galaxies that are all going to come together as the dark matter brings them all closer together through gravity, and they'll merge together, making these big collisions, sort of spraying gas and stars everywhere as they do so, and eventually sort of amalgamating or coming together into one single galaxy at the end. And you can see that beginning to form in the centre here. You have a few big clumps, a few bigger galaxies that are all orbiting around one another and gradually spiralling into one another to make a rotating galaxy in the end. And you can see this beginning to form there. I'm not going to play the whole simulation because it takes quite a while, but you can already see the beginning of spiral structure in that red patch in the centre there as the gas spins round, and that's where all the stars are going to form. And at the end of a process like this, what you end up with is a galaxy that looks something like this, a beautiful big spiral galaxy that looks really pristine and very well defined, but it's grown out of this messy process of galaxies coming together at different times and merging together to make this big galaxy. And so what we'd like to know for our Milky Way is how many of these mergers, or like building blocks, did it have? Like how many galaxies have come together over time to make the Milky Way, and when did they come along to make the Milky Way? And we then can compare that to how we see galaxies growing through a time travel approach and also through simulations, and ask if this picture is well represented by the galaxy we actually live in, and if it's not, why is it not? So can we work out exactly how the galaxy grew? So this is an image now of us looking through our galaxy. So this is real data taken by the Gaia telescope, which is a space telescope that's observing 1 billion stars in our galaxy to learn exactly where they are and how they're moving. So in this image, all the light stuff you can see is the glow coming from the stars in the image. And then you can see these sort of dusty features as well, this sort of black, darker patches. That's all coming from intervening gas and dust that's sort of obscuring some of the starlight. So this is what our galaxy looks like when we try and visualize it from within the disk. So we're looking through the spiral disk there. And if we study each of these stars in detail, we can maybe learn more about the galaxy. And we can do that by treating the stars essentially like a fossil record. So all of these stars would have formed at different times and potentially in different places. Some of them may have formed in the disk here, some of them may have been brought in by smaller galaxies that have fallen in. And if we can study these fossils in details, like archaeologists, then we can learn about how our galaxy came together. So I've just shown a picture here in the bottom left of one of my favourite archaeologists. This is Daniel Jackson from the hit TV show Stargate. I don't know if you're familiar with it, but there is like 10 seasons and 3 movies worth of stuff to watch there. So given that we're all in lockdown right now, it is a good project to start if you want to see like an archaeologist who also travels through space. But yeah, just a recommendation, take it or leave it. But yeah, so if we act like archaeologists and study this fossil record of our own galaxy's growth, we can build up a really precise picture for how our galaxy is formed. And we can do that by taking different measurements of the stars. So we'd like to know precisely where they're located, so a 3D position, so where they are in the sky and how far away they are. That tells us where they live now. And how fast they're moving, because that can tell us if they're maybe within the disk of our galaxy, perhaps they're in that central bar or bulge region, maybe they're in the outskirts in what we call the stellar halo. We can also learn from their composition and age something about where they were born. Were they born within the disk from new material that's in our galaxy, or were they brought in perhaps in an ancient merger from a different galaxy? By putting all this information together, we can build up a really beautiful portrait for how our galaxy's been forming over time. Now the downside to this is, obviously, if we could do this for every single galaxy in the universe, that would eliminate the need for the time travel approach, because we could just study each galaxy in like a forensic level of detail. But to make these kind of measurements, you can really only study the nearest galaxies to us, so things like the Milky Way, obviously, and also our neighbouring galaxy Andromeda. As our telescopes get better, we'll be able to push slightly further and further out into the universe. But at the moment, we can really only do this in our back garden. And that will then only tell us about a handful of galaxies, but they'll tell us about them in incredible amount of detail. So it's really work worth doing. So to do this, we need an assortment of telescopes. We tend to use all kinds. I'm just going to show you some images of my favourites. So this is a ground-based observatory that I use a lot. These 2 laser shooting telescopes are the Keck telescopes, located on the summit of Mauna Kea in Hawaii. They have mirrors inside. They're 10 meters in diameter, so they're really large telescopes, and they let us take not only beautiful images, but detailed spectra as well, which sort of splits up the light coming from stars so that you can measure their composition and their motion better. So we can use telescopes like this, and then we can also use an array of space-based telescopes. And so here's 2 of my favourites. On the left, we have the Hubble Space Telescope, which is a very famous telescope. We already talked a little bit about the Hubble Ultra Deep Field. So it looks at very distant galaxies, but it also looks much closer to home as well. And then on the right, we have this Gaia satellite that I told you about just a moment ago, that's taking a census of about 1 billion stars in our galaxy to learn precisely how they're moving. And this is a real game changer for the Milky Way. It's completely revolutionising how we understand our galaxy. And for galactic archaeology, it's probably one of our best tools. It can do a little bit of work for Andromeda, but the stars there are really a little bit too far away for Gaia to help us out a lot there. But it can give us some basic measurements as well for the M31, which are quite interesting and will become more interesting with time as well. All right, so what does the Milky Way timeline look like? If we combine all this data together and look at it as well with simulations and models, we can begin to understand how our galaxy has been built up over time. So this is kind of a busy graph from a paper by Diedrich Kreuzen, whose name I may have gotten wrong, and I apologize, Diedrich. And this is essentially showing us a timeline for how we think the Milky Way formed. So on the right-hand side, on that vertical axis, we have the look-back time in billions of years. So at the bottom we have 0, which is today, and at the top we have the early universe at about 12.5 plus billion years ago. Now in the centre you have this coloured bar that's moving from sort of blue to yellow, and that's telling you about how the Milky Way has been building up its mass in stars as a function of time. So by today it has the most amount of stars, in the past it had fewer stars. That's what we're seeing there. Now at the top we have a number of pictures, and these pictures are then sort of connected to this this coloured line that represents the Milky Way's growth, because we think these are the merger events that are adding in more stars to the Milky Way over time. So smaller galaxies that have been feeding into the Milky Way and making it more and more massive with time. Now, it's hard for us to go too far back into the past because we really lose some information about exactly what was happening 10 or 11 billion years ago. But we can pick out a number of different fragments of proto-galaxies that have come in and helped form our galaxy. So the most recent one is the most straightforward. So on the top left there we have Sagittarius, and I'll show you more about this at the moment, but it's an ongoing event. So we can see this galaxy being destroyed by our galaxy right now in the sky. And then as we move further back in time, we have earlier mergers that happened very early on actually in the Milky Way's history. So things like the Gaia-Enceladus merger, or the Gaia sausage as it's also known, Sequoia, the Helmy streams as well, which are potentially multiple mergers. And then an early event that's been termed the Kraken, which could be either a single very early merger or perhaps a number of small mergers that all happened at a very early time, 11 billion years ago. So this is basically the timeline for how our galaxy's formed. And one of the interesting things about that is that most of its formation seemed to happen very early on in the universe, so more than 9 or 10 billion years ago. And that's a bit surprising because most Milky Way-like galaxies, or a lot of them we think, should have slightly later mergers, so they should build up their stuff over a longer period of time. But our galaxy seems to have done a lot of its formation very early on. So that's a little bit different from what we were expecting based on some other approaches for studying how galaxies grow. So maybe our Milky Way is a little bit strange. It's not crazy, but it is really interesting that it doesn't seem to be an average galaxy in some sense. So this is our timeline, and I'm just going to go into a little bit of its details now. So I told you about Sagittarius, so this is this cool galaxy that's currently smashing into the Milky Way and being destroyed. And we can see it actually happening now, this ongoing merger or collision with a smaller dwarf galaxy. And so in this image, what I'm showing you, down the centre, that vertical band, is our Milky Way disk again. So it's just been sort of shifted by 90 degrees, and that's our galaxy as we look through it, so the stars as we look through the Milky Way. Now, perpendicular to that, you'll see these sort of bright bands which are essentially showing the density of stars in the outskirts of our galaxy. And this is actually the Sagittarius stream. And there's a little blue circle near the centre of the Milky Way there, which is the Sagittarius dwarf galaxy. So this galaxy has been orbiting around the Milky Way, and because it's so much smaller than the Milky Way has been sort of tearing it apart and ripping out its stars to make this beautiful stream that we can see sort of going all around our galaxy, covering the whole sky. So this is an example of how the Milky Way gets more mass over time. And in fact, if we look at this in more sort of a 3D approach, we can see how this looks compared to the whole galaxy. So this is an image from a simulation done by Laura Majewski about 10 years ago now, I think. So this is the Milky Way galaxy, the disk, the beautiful spiral arms in the centre. You can see where our sun is as well. Then all of these red stars are sort of the debris, the removed stars from the Sagittarius galaxy, which is located at the position of this SGR core. So as it's moving around the Milky Way, all of these stars are being spread out in these beautiful loops that tell us about where Sagittarius has been in the past. So it's sort of tracing out the orbit of the galaxy as it's destroyed by our own galaxy. So it's a really nice image of a recent merger event. Now this looks very impressive, but actually Sagittarius is significantly smaller than the Milky Way, so we would call this a minor merger event. It doesn't really add proportionally that much mass to our galaxy. So it's a small event. And we actually think that the Milky Way, maybe should have accreted something a bit more massive not so long ago, but it hasn't done. We do think it's about to have a relatively large merger soon. So we actually happen to know of a merger that's going to happen very soon with a more massive galaxy in the Milky Way. And so I'm just going to have you guess about which galaxy you think the Milky Way is going to merge with next. So I've given you 3 options. There's a Large Magellanic Cloud, there's Andromeda, which we talked about at the beginning, and then there's Triangulum as well. So I'll let you guys vote on this as well. And if my colleagues are watching, I do expect you to get this right, otherwise I fear for the future of our department. So while you have a bit of a guess here, I'm just going to look through some of the questions you've been sending in. They're all very excellent. So I'm just releasing some of those as well now. All right, so we're seeing a bit of a almost 2/3, 1/3 split here. So it seems like no one likes Triangulum for this. We're split somewhere between either the Large Magellanic Cloud or Andromeda. And the correct answer is the Large Magellanic Cloud. So the next galaxy that's going to collide with us is this little beautiful galaxy here. It's a dwarf irregular galaxy called the Large Magellanic Cloud. It has a little companion called the Small Magellanic Cloud because we are very good at naming things in astronomy, very original. And it's a sort of a star-forming small galaxy, but actually it's not that small compared to the Milky Way. Recent work that's been done by a number of people, including my colleagues at Surrey, suggests that it's a significant fraction of the Milky Way's total mass, maybe somewhere upwards of 10% of the mass of our galaxy. So as it's colliding with us, it's currently coming into the Milky Way right now. It's really changing the outskirts of the Milky Way and having a big impact on the stellar populations within our own galaxy, so where the stars are and how they move around. And as this merger continues, it's only going to have a more and more pronounced effect. So we think that the LMC, or the Large Magellanic Cloud, only fell into the Milky Way recently, so it's on its first infall, as we say, which is like its first passage around the Milky Way. And it's sort of located just south of the disk here. So this is an image now showing you the Milky Way galaxy plane in the centre again, and then the large and the small Magellanic Clouds are shown sort of in the bottom right here. And all this sort of reddy orange stuff that you see coming out from that is sort of the gas that's being pulled away from the large and small Magellanic Cloud and depositing itself into our halo. These galaxies are also losing their stars to each other because they're interacting, and also to the Milky Way as well. And as they come closer and closer to the Milky Way and orbit for longer, they'll eventually be completely destroyed by our galaxy and will add their stellar mass to our own. And it'll be interesting to see or to learn about how that will affect the structure of our galaxy in the future. Okay, so that's all very well and good, but if we're only learning about one galaxy, are we really learning about that much? So ideally, as I said before, we'd like to do this for as many galaxies as possible. Now, at the moment, we can do it for at least one other system, and that's Andromeda, this galaxy that's 2.5 million light years away. And this is the one that I've spent essentially my whole career working on, so I know it very well. And it's a beautiful spiral galaxy. In many ways, it's quite similar to our own Milky Way. They're comparable in terms of their size and their brightness. Andromeda is probably a little bit bigger, but they're very, very similar galaxies in general. So statistically, there's not much difference between them. And they grew up in the same neighbourhood as well. They're located very close to one another, so it stands to reason that they've experienced a similar kind of environmental history. So the question is then, given that we have these two similar-ish galaxies in a similar part of the sky, have they grown up in similar ways, and can we learn about the merger history of Andromeda and compare that to the Milky Way? And we can, which is really cool. And it's a bit different because as the stars are further away, our measurements are less precise. So we can't learn as much or as much precision about the history of Andromeda. But in other ways, it has a big benefit over the Milky Way, which is that we can see all of it. So living in the Milky Way kind of hampers our view of our own galaxy. We're not entirely sure what it all looks like because we're observing it from within. Whereas Andromeda, we're observing it from without. So we can see the whole picture. It's basically a big panorama. So we can image it as far out as we want to and really look for signs of past mergers and past collisions that have grown Andromeda over time. And we do that by not just looking at this beautiful central spiral here, but actually by imaging much further out, so way beyond this sort of 150,000 light years that make up the disk, and out to sort of a box that's more like 900,000 light years on a side. So this is something that we call the Pan-Andromeda Archaeological Survey, or PANDAS, and it's something that's been a survey that's been imaging these outskirts of Andromeda for a long time now, and I've been very involved with. And this is the map it's made in the end. So what you're looking at here is essentially the density of stars at the distance of Andromeda. So each of these pixels tells you about something about the stars living there, and they're color-coded roughly by how old the stars are. So those reds and yellows means the stars are probably slightly younger, and those blues and greens mean they're probably slightly older. And already we think it looks quite different from the Milky Way in a number of ways. First of all, you have all these purple spots I've put on here, these purple dots. These are all little galaxies that are orbiting around Andromeda. Now, for a given brightness, there are more of these small galaxies orbiting around Andromeda than there are the Milky Way. So that already tells us that Andromeda might be more successful at attracting nearby galaxies to help it grow over time. And then we can see all these beautiful stream features as well, and in particular, there's one cool stream here. This is the giant stream that's coming out sort of the bottom of Andromeda Galaxy to the south. That's why we call it the giant southern stream as well sometimes. And we think this has actually been formed by something the size of the Large Magellanic Cloud having already fallen into Andromeda about 1 billion years ago. Now when it did that, it deposited all this material in this beautiful stream, but also this big yellow fluffy disk that you see around Andromeda. Many of the stars there, you can see these kind of like shell features almost in the outskirts and plumes. Those are likely coming from that large galaxy that fell into Andromeda in the past. There are also a number of other streams as well that we see, so I'll just change the figure now to highlight them all. So this is now sort of outlining all the different streams that we think have come from different galaxies falling into Andromeda. And some interesting ones at the top here, you have these two streams that are NW1 and NW2. These are the northwest streams. And we think these were probably formed by things like Sagittarius falling into Andromeda. And there's two of them. So we've had maybe two Sagittarius already falling in to the Andromeda in the past, whereas in the Milky Way we're only getting one now. And we also have this large galaxy to the bottom left here, which is called Triangulum, or M33. And this is a beautiful disk galaxy that also seems to be interacting strongly with Andromeda. So you can see it has this sort of thing that has been labelled debris in the outskirts. Those are stars that are being pulled away from M33, or Triangulum. And we're not entirely sure what could do this, but one option is that M33 has already had a close passage with Andromeda. So these could be little tails from M33 passing close to Andromeda in the past. And I have a little movie here where you can see M33 doing just that. So it starts on the other side of M31, and once this movie starts, you'll see it starts to move towards Andromeda, and it gets very, very close. And that close passage means that you sort of pull out a lot of the stars from the centre of Triangulum, and you really sort of warp its outer disk. You also affect the shape of the M31 disk as well, because the Triangulum is a relatively large fraction the size of Andromeda, so it's a quite major collision or close passage there, which affects both of the galaxies. Now at the present day, Triangulum is falling back towards Andromeda, perhaps for another close passage in the future and eventually a merger. But so far it's managed to mostly survive. So that's one option for what's happened there and why we see these sort of big debris features around M33. And that's what it looks like now. Now, so that means that we learn a few things about Andromeda and the Milky Way. The Milky Way seems to have formed most of its stuff early on. So it had lots of early mergers, and maybe now it's beginning to sort of interact more by accreting things like Sagittarius and also the Large Magellanic Cloud. Whereas Andromeda seems to have been maybe a little bit more active, both in the past and recently. So seemingly attracting more galaxies to it, and maybe looking a bit more like a typical galaxy that we would expect. So it's more of a typical Milky Way-like galaxy than the Milky Way galaxy is. And that's quite interesting as well. And it's cool that in this small patch of sky, we have two similar galaxies that seemingly have quite different histories, but still end up looking like beautiful spiral galaxies. at roughly the same mass. So I think that's really, really quite cool. And we also know from galactic archaeology not just what's happening in the past, but what's likely to happen in the future. So I've already talked about how the Large Magellanic Cloud is falling into the Milky Way, Triangulum is falling in towards M31. There's also a much bigger event that's on the horizon for these two galaxies. So we've measured how Andromeda is moving towards us, and we can see that it's actually heading right at us. So if we measure the relative motion of Andromeda to the Milky Way, it seems like they're on a collision course. And there's a bit of variation in how long into the future we think this will happen, but perhaps in sort of 3 to 4 billion years, these two galaxies will become very close to one another, so close they can no longer escape one another's gravity, and they'll have to merge and become a single galaxy. And so this is what we're seeing now. So they've had their first flyby, which has changed the shape of the stars around the galaxies. But then they'll come closer and closer until they form one giant galaxy. And it won't be a beautiful spiral galaxy anymore with lots of stars forming. It'll be a massive sort of round elliptical galaxy with no new stars forming, so only with leftover stars from what was in the original two galaxies. And that merger will finish in something like 7 or 8 billion years' time. And at that point, we won't have a disk galaxy here anymore. We'll look very different. Although Triangulum, which is on the right-hand side there, may survive a little bit longer. Now, the cool thing is, if we could live for another 7, 8 billion years or so, we could actually see this changing the sky at night as we look at it. So this is some images taken from that NASA produced to sort of show how this would look over time. So if you went somewhere very dark on the planet Earth and looked up into the sky, you'd see this beautiful band of stars that is our Milky Way. So that's our spiral disk there that we're looking through from the Earth. And if you look just slightly to the left of that, there's a little fleck there, and that's the Andromeda Galaxy, which is the central part of which is almost sort of visible to the naked eye, and certainly with binoculars at the time being. But as it gets closer, we'll be able to see it sort of moving towards the Milky Way. So in a couple of billion years' time, we may see that stars sort of in the same way that we see our own galaxy imprinted on the sky. And then as they begin to merge, we'll see those two disks coming together. And when they do that, they're going to compress a lot of the gas they still have in the disks of these two galaxies, which means new stars can form. And then the sky is going to get really pretty, because you'll have all these new stars forming. Those that are quite high mass will burn very brightly for a while and then explode. You'll see all these sort of fireworks in the sky, and it will look really neat. But then once this has happened, all of the rest of the gas is going to get heated up and sort of move away from the central parts of the galaxy, and it won't be able to cool and form stars anymore. So then all these beautiful bright colours will start to go away, and we'll also start to lose that defined sense of the two disks of the galaxies as they merge towards one giant elliptical galaxy. And our sky, instead of seeing this beautiful disk pattern, we'll see more of a kind of like circular bulge or glow that's us looking through our elliptical galaxy rather than a spiral galaxy. And that's basically where we'll be in 7 billion years' time. And so that's really all I was going to say about these galaxies now. So I guess we can move to the questions. I'm just going to put a few more of them forward. Bill and Monica. Okay, so just move now to the Q&A section. And so these are the questions you guys have been asking while I've been talking at you. I think we have 14, so I'll just see if I can get through them all in the next sort of 10 minutes or so. Okay, so the first one is from Nathaniel. And could a future twin Gaia, a very long baseline, resolve M31 stars sufficiently to help also map its stars? So we're already kind of doing something like that. So not so much using Gaia, but by using first images from the Hubble Space Telescope. So we've been looking at galaxies around M31 for a long time with Hubble. And that can act as like a first image baseline. So we're looking at the stars once with Hubble. Then in the future, we'll have the James Webb Space Telescope, which will eventually launch. And then it can take images of those same stars and the same galaxies, but in sort of maybe 10, 20 years' time, away from when they're observed with Hubble. Now, in that sort of intervening 10, 20 years, the stars or the galaxies will have moved ever so slightly away from the coordinates we first observed them at. And what that means is we can measure then how they're moving in 3D space, and we will be able to get some handle, like a less precise version of Gaia for some parts of M31. So that's essentially what we will be able to do there. That's basically it. And yeah, so a better Gaia would be amazing. And I know there are plans to build sort of more precise gyres. Whether or not that will help us with M31, I think it's a very difficult thing to do, just because the further away your stars are, the slower they move across the sky. So you need very precise instruments to measure that. Gyres are already phenomenal. Okay, so that's that question. I sort of already answered David's. Yes, I do use that as a chat-up line. What is the perpendicular stripe to the stream on the right? So this probably was from the M31 images, I think, where you have that giant stream coming down and almost like those arcs coming out from the side. If it's not, please just ask the question again and I'll explain what you actually want me to explain. And we don't actually know what forms those sort of perpendicular streams coming into the giant southern stream. One of them, my PhD student Janet, was studying to see if it's perhaps showing us where the giant stream came in from. And some of the others may be either formed from smaller galaxies that just happen to sort of orbit around the same space in the sky, or it could be shells. So as the giant southern stream galaxy smashed into M31, it may have sort of blown out some of the stars from the M31 disk and formed these kind of shell patterns that look a lot like streams. So that could be why, or what they are. Bill and Monica, as you know, what the very, very bright star in the sky at the moment is probably still Venus, and it's probably still what you're looking at. The next question is, why are galaxies everywhere? Well, so we just think that they're everywhere because that's just kind of how the universe has been forming. So initially, when you have the Big Bang, you have these parts of the universe that, because of the early quantum fluctuations, are slightly more dense in some parts of the universe than others. And these little tiny overdensities gradually grow in size, so they'll become small galaxies over time, and then bigger galaxies as more and more of them merge together. So this will be happening all across the universe, so you end up with just a lot of different galaxies, just because the universe is vast. Now, many of these galaxies will come together over time and merge together, but the universe is also expanding, so they can't all come together, so you'll always have a lot of galaxies. Although we probably have fewer now than we would have had at the beginning of the universe when they're all smaller and forming by themselves. So hopefully that was helpful. So if Earth could be part of the Large Magellanic Cloud, would our planet survive after being absorbed by the Milky Way? Yes, actually, we think so. So this is sort of the same for when we have the collision with Andromeda. So Andromeda is a massive galaxy. It's slightly bigger than the Milky Way, and so when these two galaxies come together, all the stars are going to move around the galaxy. But it'll happen in a relatively slow way, and space is mostly empty. So our star and our Earth probably will just move their position in the galaxy without really changing anything locally. So the Earth will be fine. And the same for if it was in the Magellanic Cloud. So probably most stars and most planets will be unaffected other than the positions that they now live in with respect to the rest of the galaxy. Okay, now from David, is there a fact about space that still blows your mind in spite of the fact that what you have studied, what's out there for years and years? I mean, there's loads of them. I'm trying to think of a good one. So, I mean, I've been talking a lot to school kids this week about some cool stuff about the solar system. And I still think it's amazing that, the giant red spot on Jupiter is this huge storm system that's been raging there for a long time. And that whole storm is the same size as our entire planet. So that blows my mind. And then if you took the moon, the distance between the moon and the Earth, you can fit all of the planets in the solar system between those two objects. I think that's pretty cool. Space is incredibly empty. Everything is really big. And if you think too hard about how big it is, you do start to go a bit nuts, I think. So you kind of have to, we throw around these big numbers all the time in astronomy, and I feel like if you think too hard about them, you realise just how small and tiny you are. And how short a time we've been here for as well compared to the rest of the universe. The universe is 13.77 billion years old. Humans have been around for a tiny fraction of that time. So the universe has been going on without us for a really long time, which I think is just kind of amazing. Okay, next. So yeah, lots. I could go on for ages. I probably shouldn't go on for ages. Corin, how did the Planck survey predict the timeline of the universe? So the Planck survey studied the cosmic microwave background, And essentially you can analyse this radiation and how the universe has been cooling over time to figure out how long it's been since that radiation was released and what that means for the timeline of the universe. I think that's kind of the most straightforward way I think I can explain it, and then there's probably something much more complex to it than that as well, but just by measuring how that radiation changes with time, how the temperature changes with time, you can get a good handle on the age of the universe if you know about what the universe was constituted of, so when it was radiation dominated and matter dominated. So that radiation really gives us a really strong idea, and so by measuring that radiation and mapping it very accurately, we can figure out how old the universe is. And it can also figure out we can apply models then to figure out what the universe is made of. And so it can't tell us as much about the galaxies, so we have to learn about that from other observations as well, but the age it can pinpoint for us really nicely. Could streams help map the dark matter around the Milky Way? And yes, they could. So this is the whole talk that Dennis, my colleague, should probably give on YouTube at some point. But yes, so these galaxies, as they're being destroyed by the Milky Way, they leave behind these beautiful streams. So I showed one today, the Sagittarius stream, but we see lots of these streams around our galaxy. Most of them are much smaller than Sagittarius. But because we think dark matter is kind of clumpy, if you have a beautiful stream of stars, a dark matter halo with no stars in could occasionally punch through that stream and make a little gap in that stream. And so we expect this to happen. 2 streams in the Milky Way, and my colleague Dennis uses those streams and tries to find the gaps in them in order to put a constraint on how clumpy dark matter is and what the dark matter particle could be made of. The next question is a throwback to last week and asks if the Large Magellanic Cloud killed the dinosaurs. That is not a theory that's been put forward. I suspect it wouldn't have done. Because the LMC doesn't really have that kind of period that we talked about last time. So it's just a galaxy that's infalling now. So it probably has no effect on the dinosaurs. They were safe from the LMC, I think, just as we are now as well, which is good news for all of us. Okay, Bill and Monica, the numbers and scales that you work with are mind-boggling. How do you manage to rationalise them? Well, yeah, no, that is, as I said, kind of one of the big things about this is that it's quite hard to do. I think you just get a bit blasé about it. Like, we just throw the numbers around as things like, that's just like 5 times 10 to the 12. And if you say it like that, those are all normal numbers, like 5 times 10 to the 12. But really what that means is a 5 followed by 12 zeros. And if you had to write that down every time, I think then it would be harder to rationalise. But by expressing them in an exponential way, it's much more comfortable. And yeah, after a while, you just get so used to talking about that kind of scale that things like, one solar mass, like one mass of the sun, you're a bit like, well, it's just very light, isn't it? So you kind of get a bit blasé, I think. You just get too used to the big numbers. Okay, so Monica asked a question about Venus. That's good. From Nathaniel, does the cosmic microwave background radiation have any imprint of a distribution of dark matter? Yes, we think it does. So the way that we see, so basically, the cosmic microwave background is overall very, very smooth. So the temperature of the sky, if we look in all directions, is almost perfectly uniform. So it's about minus 270 degrees Celsius or 2.73 kelvins across the entire sky. But there are these tiny, tiny little fluctuations in the temperature. So at the order of sort of 1 in 100,000th of a degree or something, these little tiny changes in the temperature as you look across that map. And those temperature fluctuations are actually telling us about how the material in the universe was distributed at early times. So it tells us about the density of the universe at early times. And those fluctuations we were expecting to be larger if the universe was composed solely of ordinary matter, by about sort of 2 orders of magnitude, I think. 2 or 3 orders of magnitude, I forget exactly. And so if the universe is only formed of regular matter, those changes in temperature should be larger on the sky. And the fact that they're not tells us we need something like dark matter that can grow very early in the universe without being affected by the fact that the universe is incredibly hot, which stops ordinary matter from growing at very early times when the universe is very hot. So from that we can learn about the dark matter by measuring how much stuff there is on different scales in the sky as well. That can give us a good handle on the dark matter as well. Yeah, so we can learn a lot about the distribution of dark matter from the cosmic microwave background. It gives us kind of our initial conditions for how we think the universe looked in terms of the dark matter and regular matter at very early times. Okay, and what is the current age of a universe edge if expansion has taken us away from this. And so this question is kind of complex. So we don't really know what it means to be at the universe's edge. The universe appears to be infinite and expanding in all directions. So there is no real edge and there's not really a centre. And the universe itself is 13.77 billion years old. So all of it is that age. But some of it is much further away from us now because of the expansion of the universe. So because it's expanding with time, we can see light from galaxies that now should be outside of our observable horizon because of the light travel time. But because the universe is expanding, they were closer to us. Well, the light has had to travel less far than the actual distance between us and the galaxies now. So yes, the age is 13.77 billion years everywhere in the universe. Okay, and then the last question, which is probably where I got the streams wrong. So on the Milky Way image with the bright stream, there's a perpendicular one. Okay. So this, I think, is when we were looking at Sagittarius. So that may well be the orphan stream that cuts through Sagittarius. So I'll just have a quick look back, actually. This is the last question. I can go back to the presentation. And hang on, I'll just go back to the Sagittarius slide. So that is this one here, I think. So on the right hand side, I think you're talking about, so I think that could be the orphan stream. I'm not entirely sure of all my Milky Way streams. I know the Andromeda system much better, so someone else could probably tell me if I was wrong. But there are a number of streams we see there. There's a very famous image put together by Vasily Belokurov of that patch of the sky on the right side called the Field of Streams. It shows you lots of different Milky Way stream structures that are coming through the Sagittarius. Well, at least they're overlapping with the Sagittarius stream in projection, not necessarily cutting through them. But yeah, so it's probably a smaller stream from a smaller dwarf galaxy that has also been stripped and is adding its mass to the Milky Way as well. All right, so that's basically everything. The last thing I was going to say is that I was planning on doing another talk a week on Thursday, and it's for two reasons. There are like two important birthdays happening next week. Both my birthday on April the 23rd, which is where I'd be giving the talk, because I have nothing else to do on my birthday in lockdown. And it's also the day before Hubble's 35th birthday, which happens on April the 24th. So I thought I might give a talk on sort of the history of the Hubble Space Telescope and all the amazing science it's done. So if you're interested, I'll probably do that in just over a week and a half's time.